Hi, everybody. Welcome to the Shiko Math Practice Lab, Learning Through Practicing. And today, we're going to finish this unit and limits, continuity, and the differentiability unit. And we are at our last practice set, set number 6. And in this practice set, we're going to practice how to determine a function is differentiable at a certain point or at a certain interval or not. Okay, so here are the 6 problems we're going to work. So the group 1 problems here just give you a set, different functions, and we're going to determine what value of x is differentiable and what is not differentiable here. Okay. And then the group 2 is a very special function. We're going to determine if the f prime 0 exists or not. Okay, as always, it's a good time to pause the video and get your pencil and the paper out and try to work some of those problems by yourself first. So when you finish, and then come back and resume the video, and we can work the problems together, and you can check your answers. All right, so if you like the video, don't forget to subscribe it my channel, and also at the end of the video, if you still get confused or you still have questions, feel free to leave me a comment and I will try to answer. Okay, now it's a good time to pause your videos and then we'll come back. So I'm going to the whiteboard and I will talk to you later again. Okay. Okay, so I'm back, and I hope that you got a chance to work some of the problems and get a feeling about it, right? So remember, this is the last practice set in this unit, and we're going to talk about the differentiability. On the practice set number 5, we use the limit approach to find the derivatives, and that's the definition of the derivative. So today we're going to talk about the differentiability. As always, I'm going to do a brief review about what is the differentiability. So differentiability basically is you want to see a function is differentiable. You can say it is differentiable on any specific intervals, or you can check to see a function is differentiable at a specific points here. Okay, so we're going to review the few things here. The first, we know the f prime x is here, right? So from the practice set number 5, we know you can say this is from h approach to 0, then fx, then this is x plus h, and the minus f of x. So if this limit exists, then we say f prime exists. Or if you want to see, at any specific point, x equal to any specific point, then you can use this limit definition, right? So x approach to a, and then this is x minus a, and f of x, and the minus f of a. So if those exist, right? So if we use the limit definition, if those exist, then we say it's differentiable. Okay, and I think also your teachers also we said there are a few cases it's not differentiable here. I don't know you still remember or not. Okay, so we're going to do some of these examples here. So the first one's here, case number 1's here, the situation number 1, right? Situation number 1 is when you have a corner. Okay, so what I mean when you have a corner, so for examples here, right? So when you means you have a corners here, that means if you have functions, it's something like this, right? So this one's here, when the x equal to a, you have a sharp corners here. Then I know this function is not differentiable at a. Okay, so the next one's here, so this is the corners, right? Okay, so the next function is not differentiable, is, okay, so now the differentiable is if your function is at the jumping points, right? So like if your function, oh, oops. Okay, so if your function is like go like this, right? And then here, then you can show like this, right? So here is A. So your function have a jumping points here. Then this one's here. This is our second situation. Is have a. So what do we say if you have a jump discontinuity? So if a function is not continuous, then it's not differentiable at this point here, right? Okay, then the third one is here. Some of students might not be very familiar with. And this is one we call it is the vertical tangents. So what is the vertical tangents? It's something like this. Okay. Okay, so let me, I hope I can draw it good. So it's like, okay, so this is A, see here, right? So when I mean the vertical tangent, that means here, you have a tangent line. It's kind of like it's a vertical. So it's a, you have a tangent line. Oops, don't move over here, right? Oops, let's move here, right? Okay, okay, try to get a better graph here. So if you have a vertical tangent line, then this is not, you know, it's not differentiable. So basically, that means the limit here, when the x approach to a, then the f prime x here is going to the infinities, right? Okay, so those are the three situations. So we're going to take a look at our example, and then we decide, you know, which situation we are dealing with, and then you will see that. Okay, so now we have a 6 problem. So let's go ahead and start. Okay, the first one's here, this is f of x is equal to the x minus 6. So if you know, if you remember, you know, from your algebra class, is here, right? X minus absolute value of the x minus 6 here. Okay, so if this is 6, right? Okay, so what is your function going to look like? Your function going to look like something like this. Right? So that's what is the absolute value function. So what it looks like. So as like we talked about before, so here we have a sharp corners here. So when we have a sharp corner, so I know the function not the derivative not exist. But today I'm going to show you why. So okay, so the kind of the refresh your memory. And so this is f of x equal to the x minus 6 absolute value. So we know the how to break the absolute values, right? We did this in our limit sections here. So this will be x minus 6 if x is greater than or equal to 6. And this is 6 minus x here if x is less than 6. So if you only look at each different intervals here, it is differentiable, right? So the derivatives of the top interval, you know, if you use the derivative definitions, will be 1, the derivative is negative 1. So now let's take a look at why at equal to 6 is not differentiable. So let's take a look at the limit x approach to 6, right? So I'm using my definitions here. So this is will be f of x minus f of what? minus f of 6, right? And x minus 6. And then here, I'm going to look at x is from the right-hand side. Okay, so if you take a look at the x is from the right-hand side, that means x greater than 6, right? Okay, so if x greater than 6, I have x minus 6, correct? Then the f6 is just 0, and then this is x minus 6. So what happens here? Cancel, cancel. So what is the limits for here? Limit is 1. Okay, so let's take a look. Limit x approach to 6 from the left-hand side. So this is f minus 6, f of x minus f of 6. Okay, so let's take a look again. X approach to 6 from the left-hand side. Okay, because it's less than 6, right? So the way we break the absolute value, the x minus 6 absolute value will be 6 minus x, because because it is approach from the left-hand side. Okay, so now minus 0, then the bottom still is x minus 6. So if you rearrange it a little bit, so this is a 6 minus, okay, so this will be negative x minus 6 and x minus 6. Then you cancel, get a negative 1. All right. So because here, remember this limit and this limit, right-hand side limit is not equal to the left-hand side limit. Okay. So I know limit not exist, right? Because limit not exist. So the f of x is not differentiable. At x equal to 6 here. Okay, so all the other is, so if it's greater than 6, the derivative will be 1. If it's less than 6, it will be negative 1, but at the 6 is not. Okay, so the next one's here, right? So remember we saw this function many times. What type of function this one? So we said this is the greatest integer function, right? Okay, that means you find the integer. So if it's a 0.001, you find the whole number less, the largest whole number less than the value inside. So also like from the, like our limit sections, we know what is the graph looks like here. If you don't remember much, maybe you want to review the limit section about the, about this greatest integer functions, right? So this is greater integers functions here. So for these ones here, if it's 1, 2, 3, and this is like -1, -2, right? So we know this function is a function something like this. Right? Okay. So this function, so what happens to this function? It has what? Jump, discontinuity. Right, so it has a jump, discontinuity. So we know the jump because the limit not exists. So what? So f is, where is the jump? It jumps at the whole numbers, right? So f is not continuous, right? So f is not continuous at the integer. So we know f is not what? So it's not differentiable. Right? At the integers, right? Okay, and because of f is a constant, right? So like between here is 0, between here is 1, right? So since f is a constant on open interval, Okay, so content A, so the f prime A is equal to 0. So we know the f prime x will be equal to 0 when the x is not integers or is not a whole numbers here, right? That's what we talk about is differentiability. If you have a corner, if you have a jump discontinuity, so if a function is not continuous, then it's not differentiable at that point. But the backward doesn't mean if a function is continuous, it doesn't guarantee it's a differentiable, just like absolute values, right? So this is a continuous function, but it does not guarantee that x equal to 6 is differentiable. So be very, very careful. Okay, so now let's take a look at the next ones here, right? Okay, so the next ones here, so this is f of x equal to the f. So this is f of x equal to the x times the absolute value of x is here. So this problem also we need to know how to break it, right? Okay, so this one will be equal to x squared if x is greater than equal to 0, right? Why? Because if it's greater than equal to 0, absolute value of x equal to x, so x times x is equal to x squared. If this one here will be x squared, negative x squared if x is less than 0. Why? Because we mentioned many times absolute value of x is equal to negative x if it is less than 0, right? So you need to remember this, how to break the absolute value. So we have this ones here. Then from here, we know the f prime x is here. If you just focus on each interval, this one will be 2x. You know, for the x is greater than 0, this is negative 2x if x is what? Less than 0, right? Okay, so now we are going to see. So this one we know. So now the only thing we need to see, you know, at this jumping point, you know, like this piecewise function here and x equal to 0, because I know this is a polynomial, this is a polynomial, they're all going to be continuous. But how about at this breaking points, right? So that means that's why I need to show the f prime 0 to see if this one exists or not, right? If it exists, then we know it is differentiable at x equal to 0. Okay, so now let's take a look. Is this exist or not? So that means I using my limit definition. That means x approach to 0. This is x minus 0, f of x minus f of 0, right? That's from our definition about the derivative. Okay, so now let's take a look. This one is pretty cool. So this is x approach to 0, right? So this is x. So f of x is what? X of the absolute value. F of 0 when x equal to 0 is 0, right? So this is limit x approach to 0. Then what happens here? This x cancels, right? So what do you have here? You have absolute value of x. So when x approach to 0, what is the absolute value of x? This one approach to 0. Oh, wow. So the f prime 0 is equal to some values here. So I know f is what? F is differentiable at 0. And because they is already differentiable, you know, in the both, right? So I know in here, because it's differentiable is 0, so f is differentiable at all the real numbers, right? So it's pretty cool. So now if you say, okay, if you combine it, in fact, you can rewrite this one. You said f prime x will be equal to what? You can say this one here will just be equal to 2 of the absolute value of x, right? Because when x greater than 0 is here, less than 0 is here, right? So it's pretty cool, okay? I like this problem very much, and it show you, you know, how you decide its differentiability is, you know, it's differentiable or not. Okay, so now let's take a look at this one here, right? So they cannot tell us. So we want to see is this one is differentiable at any number or not. So we'll say, okay, let's try to find any number f prime a here to see we have any restriction. So you have x approach to a, right? So this is x minus a, and this is f of x minus f of a. Okay, so now you say here limit x approach to a. So this is x minus a. Then this is x to the 1/3 minus a to the 1/3, right? Okay, so you say, okay, if you put x equal to a, it will be 0 over 0. So we need to do something about it. So let's see. So this is x approach to a. So this is x 1/3 minus a to the 1/3. Okay, so remember the x, right? So because here you have 1/3. So x is really equal to x 1/3 to the what? To the third powers, right? And the minus a, the 1/3 to the what? To the third powers here, correct? Okay, so now this is a limit x approach to a. And then here, this is x 1/3 minus a 1/3. Do you remember? I think we talked about this like a cube minus b cube, right? Okay, so a cube minus b cube. So what is the formula? Everybody still remember? So it's a minus b. This is a squared plus ab plus b squares, right? Okay, so now I can write this one will be x 1/3 minus a 1/3 parenthesis x a squared will be x 2/3 plus x 1/3 times a 1/3 plus a 2/3 here. Okay, now see here, boom, boom, these two cancels, right? Okay, so now I have a limit x approach to a. So this is 1 over x 2/3 plus x 2/3 a 1/3. Oh, this is 1/3, 1/3 plus a to the 2/3, right? Okay, now you replace the x with a. You replace x with a, right? So you replace the x with a. So what do you have here? So you will have, okay, so you will have, okay, so here, this one will be limit x approach to a. So you will have a to the 2/3 plus a to the 2/3 plus a to the 2/3. So how many you have here, right? So, okay, I shouldn't have this limit already applied. Okay, so I will have, so what is my answers here? My answers here, this will be 1 over 3 a to the 2/3, right? So a can be any numbers, right? So this is my f prime a, see here, right? So this is my f prime a. F prime a is equal to here. So f prime a exists for all the value, except for which value is not exist when a equal to what? When a equal to 0, right? So we said exist everywhere except a equal to 0. So that is why we can say, so we said f prime 0 does not exist. Okay, so it's a different approach here. So in here, I don't know, so I just use a general number and to see which a is not, does not exist, right? Okay, so now the last two problems. This one, those two problems are very interesting, the problems here, right? Okay, so this one's here, let's take a look here. I want to find, so basically the group problem number 2, they ask us, is the f prime 0 exist or not, right? So that's what we try to find. Is the f prime 0 exist? Okay, so Okay, so now let's take a look. Just so we always back on our definition. F prime 0, that means it's limit, right? So the limit h approach to 0, then the f of 0 plus h minus f of 0, then the h is here. All right, so this is the limit h approach to 0. So this is h. So this one's here is f of what? H, right? So you put the h as your x. So this is h sine 1 over h here. Okay, so now the f of 0 here is defined on the second part of this piecewise function is equal to what? Equal to 0. So here you minus 0. So this one will give you limit h approach to 0. So this is h sine 1 over h, right? Okay, so this is a boom boom h cancel. And so this one's limit h approach to 0 sine 1 over h. So as you know, when the h approach to 0, these numbers, right? And you can approach to 0 from the positive or negative. So this number is jumping around, right? So this number, so the whole thing here is jumping around between the 1 and the negative 1. I don't have a limit to converge to. So that's why I said the limit not exist, right? So because f prime 0 is defined as limit, so if a limit is not exist, that means f prime 0 is not exist. Correct? If it's not exist, that means what is here? That means f is not differentiable. At x equal to what? At x equal to 0. Okay, so now let's take a look. The second one is here. The second one, very, very similar. The only difference is here. I have x squared instead of just x here. All right, so let's take a look. I want to find f prime 0. Okay, so the same way, the f prime 0 is equal to limit h approach to 0. And then here, the same way, so this is f of 0 plus h minus f of 0. That's right? Okay. So now, this one's here will be equal to limit h approach to 0. Now this is h. So this values here is h, right? So you plug back on your function. So this is h squared sine 1 over h. And then this values here, f of 0 is the second part. So this is equal to 0. So this is a minus 0. So this is a limit h approach to 0. This is h. So this is h squared sine 1 over h. So I can cancel our h's here. So I will have a limit h approach to 0, then h sine 1 over h. Okay, so now I need to decide if this limit exists or not, right? So how to decide it? Okay, so first things I know the sign doesn't matter what is inside. The sign is always what? Always is between 1 and what? Negative 1, correct? All right, so if you times the absolute value of h on the both sides, so this will be correct? Okay, so now I will see here, okay, so now the limit when the h approach to 0, and so I know, so this, okay, so now let's do this here. Now I take the, so the, now we will take the limit h approach to 0 on all the 3 terms. Okay, so that means it's a limit h approach to 0, negative h, less than or equal to limit h approach to 0, h sine h, 1 over h, is less than or equal to limit, and h approach to 0, absolute value of h. So take a look here. Take a look here, right? So this limit, what is this limit going to? Approach to 0. What is this limit going to? This is approach to 0, right? So by the, okay, so we call this a sandwich theory, or some people call it a squeeze. Okay, so by sandwich theory or squeeze theory, so I know the limit h approach to 0, the h sine 1 over h will approach to what? Approach to 0. So I know here, what is the limit? Limit is exist or not. So its limit is equal to 0. So exist. Right? So that's why f prime 0 is exist. If it is exist, what's that mean? That means f prime 0 exists. Right? If f prime 0 exists, what does that mean? That means f is differentiable at x equal to 0. Okay, so that's it. When we talk about the differentiabilities here, so basically you just try to use the limit definition. So the f prime x is equal to like limit h approach to 0, fx plus h minus fx over h, to see this limit exists or not. And so we also know, from the graph, we can identify the differentiability not exist, could have a corner, or could have a jumping discontinuity, or have the vertical tangents lines here. That means that if you let the x approach to a for the f of x, it will going to approach to the infinity here. All right. So let's try to remember that. So the one thing is very, very important here is a function. If it is, if it is different, if it is differentiable, then the function has to be continuous in order to be differentiable. Okay. And well, I said if a function is differentiable, then it has to be continuous. Right? If you have a discontinuous function, it's not differentiable. But a continuous function doesn't guarantee it's differentiable, right? Like the absolute value is a continuous function, but it's not a differentiable. And that is corner points here, right? So that's why I said you have to be continuous in order to be differentiable. That's very important. If it's differentiable, then it's guarantee is continuous. But if it's continuous, it doesn't mean the always differentiable here. But if your function is discontinuous, it's not differentiable at that point. All right. So if it's differentiable, has to be continuous. But if it's continuous, it doesn't guarantee it's differentiable. So here. Okay, so that's the three levels we talk about. The limit has to exist, the continuity. The continuity is the prerequisite for the differentiability, but it's not to say if it's continuous, then it's definitely differentiable. It's no. We know if it's not continuous, it's not differentiable. So, right? So it's a very, very important concept. But if it is differentiable, then it has to be continuous. Right? So the differentiability has the tightest requirement, then the continuity. Then the continuity have a tighter requirement than the limit exists. Okay, so that's why I put these three topics in one unit. Just want to make sure you understand how we're progressing from define the limit, then we go to define the continuity, then we go to define the differentiabilities here, right? So the one of the common problems of students typically get confused is if it's continuous, doesn't guarantee it's differentiable, okay? But if it's differentiable, the function has to be continuous. But if a function is not continuous, then it's definitely not differentiable. All right. So don't forget practicing, practicing, practicing. That is the way you are getting better in the math. All right. So if you like the video and you think it's helpful, please feel free to subscribe it and subscribe my channel. Also, if you have questions or you're still confused, feel free, leave a comment and I will try to answer your question. Okay, it's nice to talk to you. We finally finished this unit. That's great. We're going to start a new unit next time. All right.